Section 9.10, the ideal dilute solution. So first, what's the difference between the ideal solution and the ideal dilute solution? In ideal solution, you have two components, A and B. The attraction between A and B is the same as that between A and A and that between B and B. In the ideal dilute solution, again, let's say you have two components A and B. We don't even care about the attraction between AB or AA or AB, as long as the concentration of one of these two components is really small. For example, if you have 99% A, 1% B, that's an ideal dilute solution. Well, this is because for each A in the solution, it's surrounded by other A's, just like impure A. However, for the solute, well, there's a different story. Impure B, each B is surrounded by all other B's. But in this ideal dilute solution, because of the very low concentration of B, each B is surrounded by A molecules. So in short, in an ideal dilute solution, this chemical surroundings or chemical environment for A remains unchanged. For B, it's completely different. So that's the difference between the ideal solution and the ideal dilute solution. In the ideal dilute solution, for the solvent, we can still use Raoult's law because this solution is awfully close to pure A anyway. So we just use this equation. The partial pressure of the solvent is equal to pure pressure of the solvent times the mole fraction of the solvent. But remember, for ideal dilute solution, this X is very close to 1. It's 0.99 something. For the solute, different story. Now it's surrounded by solvent molecules, as opposed to in a pure B liquid, it's surrounded by other B's. Now it's surrounded by A's. So the environment is different. We can still use a similar equation, but we have to make some change. The partial pressure of the solute is still proportional to the mole fraction of the solid. That makes sense. But this time we need to have this X multiplied by this Henry's constant. This is the Henry's constant for the solute. This is a constant, but it does depend on the nature of the solute and the nature of the solvent. And remember, when you have only 1% B in 99% of A, you really have to look at the AB attraction now in the solution and compare that with BB attraction in pure B. Alright, that if the attraction differ by a lot, then this one differ from this pure solvent vapor pressure. They differ by a lot. So this Henry's constant will differ from this chemical vapor pressure of B a lot. Now let's look at the activity of the solvent and the solute. First, the solvent. The activity of the solvent, again, is just the actual pressure of the solvent divided by the vapor pressure of pure solvent. That's very simple. What about the activity coefficient, gamma? Gamma is simply activity over the mole fraction. Both A and X are unitless. This X is the mole fraction, and this A, I view this A as the effective mole fraction. Now in an ideal solution, we can use this equation because gamma is 1. A is equal to X. In a real solution, well, A is different from X. A is gamma times X. And then you use this equation. Instead of X, you use A, the activity, to determine the chemical potential of this solvent I in the solution. What about the solutes? For the solute, you're going to see there's a different reference.